Okay, so now we're gonna move to section 2 in chapter 3, and now we're gonna talk more from not just we're still gonna have to know how to graph the linear inequalities, but now we're gonna use it into an actual problem. And this text entitles this section a linear programming problem. So here's the problem that we kind of have here. It says a furniture manufacturer makes two types of furniture, sofas and chairs, sorry, chairs and sofas. The manufacture of a chair requires 6 hours of carpentry, 1 hour of finishing, and 2 hours of upholstery. So this is just something for a chair that makes. So the manufacture of a sofa requires 3 hours of carpentry, 1 hour of finishing, and 6 hours of upholstery. Each day the factory has available 96 labor hours for carpentry and 18 hours for labor for finishing. Sorry, 18 labor hours for finishing and 72 hours for upholstery. The profit per chair is $80 and per sofa is $70. How many chairs and sofas would be produced each day to maximize the profit? So this is more of a business type of stance as to here's our materials, meaning that here's the type of time we have to put into making these. And we basically want to say, how can we maximize the profit each day? And that should be your goal as a business person. All right. So first off, we like to put it in a table for everything. So I'm going to lay this out for you, and you can copy this table down. So for a chair, again, there's our carpentry. It takes 6 hours. For finishing is 1 hour. I'm reading down that column of chair again, and let me see if I can get my laser pointer here. So I'm reading right here. Okay. So there's a chair, 6 hours, 1 hour, 2 hours, and the profit is $80. Sofa is 3 hours of carpentry, 1 hour of finishing, 6 hours of upholstery, and a profit is $70. The available time we have for carpentry is 96 hours that we have. Finishing is 18 hours, and upholstery is 72 hours of labor. These are all of our times that we can maximize for here. So you can see that what we're going to have is we have three constraints. We have carpentry constraint, we have a finishing constraint, and we also have an upholstery constraint. So we're going to translate them to mathematical language. That's what we need to do. And the second thing is we're going to let X be the number of chairs and Y be the number of sofas manufactured each day. Now, it doesn't matter which one we make which. However, for us, this is what we're going to do. So this is how you can follow along. And there's a little bit more of the constraints that we have here. So let me start with the carpentry. So the carpentry is the number of labor hours per day. So how do we figure that out, right? Just carpentry alone. So the first thing is we have to know about how about per chair. So the number of hours required per chair times the number of chairs per day. Then we also have to talk about not just chairs, but sofas. So how many hours required for the sofa against how many hours or how many sofas we do for the day. All right, so we have to add these together. So let's just remember that if we go back to our table, the number of hours required per chair is 6 for carpentry, and the number of hours required for sofa is 3 hours. And we let chairs be our X value and sofas be our Y value. So we end up with something that looks like this. Okay. And we need to make sure that the number of labor hours per day is less than or equal to the maximum that we have available. Right. So the number of labor hours that we're going to put into this is our literally basically our 6x plus 3y expression that we have right above. And then the maximum that we have available is 96 hours that we have. So our first constraint for carpentry is 6x plus 3y less or equal to 96. Again, I'm going to explain again. This 6 is because it takes 6 hours for a chair just for carpentry. Then it takes us 3 hours for a sofa for carpentry. X is our chairs, Y is our sofas. And then we have to make sure it's less than or equal to 96 hours per day. Of course, we want to say if we have 96 hours, we're going to maximize that 96 hours, but that's not always possible, right? Those values don't always go into that 96 hours exact. Our next constraint now, and actually our next two constraints, talk about our finishing constraint. And our finishing constraint, if you look at it, we have here, if you look back what we had in our table, and then our upholstery constraint is the 2x plus 6y is less than or equal to 72. Now, we also have one more constraint, and that's our values on our chairs and sofas, because we want to make sure, and this might sound really silly, but we want to make sure we're building positive values here, meaning we want to make sure that we're actually building sofas and chairs each day. So we want to make sure that they're not negative. So the other constraint we have to throw in there is that our chairs and our sofas have to be greater than or equal to 0, the numbers that we build for the day. So the objective is to maximize our profit. And in fact, it says optimize profit, the same thing. But that is what we're trying to do. Into mathematical language is what we have. We have the profit. Our total profit comes the profit from chairs plus the profit from sofas. Remember, our profit per chair is based on how many actual numbers of chairs that we create. And then our profit from sofas is also multiplied by the number of sofas that we create. So profit per chair, this right here is 80. Right, the number of chairs for us was the value X, the variable X. Profit per sofa was $70 profit, and then the numbers of sofas we said was going to be our variable Y. So this is what our profit equation or expression or inequality will end up looking like. So linear programming problem. So we have to look at now, we have to write all of these constraints into one, all of them. And this last part, we're really going to focus more on the next section, but we need to find values for X and Y for which our expression of 80X plus 70Y is as large as possible, because we want to make sure that we maximize our profit each day. And so here are all of our constraints into one. This is where we get called linear programming. So our production schedule, in the manufacturing problem, each pair of numbers are X and Y, any point that's on there, satisfies a system of inequalities is called a production schedule, meaning that this is what we're on schedule to make each day to maximize our profit. So the first thing is here's an example here to talk about production schedule. Which of the following is a production schedule for, here's our system. So is 11.6 a production schedule? Meaning, again, remember, X and Y. And if we go back, our X and Y, here, right here, probably a little better. X were our chairs, Y were our sofas. So can we make 11 chairs and 6 sofas? Can we make 6 chairs and 11 sofas? So how do you figure that out is you're going to take these values, just a simple way of doing this without a graph. You're going to take these values and substitute them in for X and substitute them for Y. Well, if we take this 11 and 6, so this means 11 goes in for X, 6 goes in for Y. This does satisfy our constraint because 11 times 6 is 66, and 3 times 6 is 18. And if we add those two together, 66 plus 18 is 84, which is less than or equal to 96. So we have enough time to make 11 and 6. Now we talk about here, 11 plus 6. Okay, 11 plus 6 is 17. That's still less than or equal to 18, so it satisfies this constraint. And then we have 11 and times 2, which is 22. And then we have 22 plus 6 times 6 is 36. This gives us 58, which is still below this threshold of 72. So it satisfies all three of these constraints, satisfies the X constraint if it has to be bigger than 0 or equal to, and the Y constraint that has to be greater than or equal to 0 as well. So this satisfies all of this. So this can be part of our production schedule. And when we check 6 and 11, I want you to do that on your own and then see what you get. So go ahead and pause now and come back. And what you should see is that our first one was yes, but this one is no. And the reason why this one is no, you don't have to go very far, because if you substitute a 6 right here, this gives you 6 times 6, which is 36. And then 11 times 3 is 33. Right? So 6 times 6 is 36. Sorry, I lost track of what I'm doing. And then 3 times 11 is 33. That gives us 69. Still fine. 6 plus 11 right here is still below this 18. And then 6 times 2 is 12. And then 11 times 6 is 66. And here is where it faults to be 78. And 78 is not less than or equal to 72. So it satisfies these constraints. It definitely still satisfies the positive constraints, but it does not satisfy this. Therefore, it cannot be part of our production schedule. We cannot make 6 chairs, 11 sofas. So what a factory tries to do is it tries to say, we want to make sure there's no waste in our labor. We want to make sure that all day, every day, everyone's working and we meet our quota as much as we possibly can. So how we do that is by looking at the system with just as equations. Okay, so we want to say no waste. And in order for this to be no waste, if we were to graph these three equations, then that means they would all have an intersection point. The exact same point, they would all intersect. So if I was to graph all of these, we can use our standard form, we can use slope-intercept form, however you want to do it. But here's the graph, and you can see that this does not, these two lines intersect here, and these intersect here, and these intersect here, but all three lines do not intersect in the exact same spot. So therefore, according to the graph of the three equations, there is no common intersection, therefore no solution. We are going to have time wasted in completing what we're trying to do for the day. So next we have our feasible set, which we talked last section. And this is where it satisfies all of our constraints. And I'm going to show you in the graph what it looks like. So here we're going to go to our feasible set. And I'm going to graph each one separately, one at a time on the same graph so you can see how this starts to transform. So first, we're going to graph the boundaries. So the very first graph that we have, I should say, let me ask you to do this. Before I get into that, why don't you take the time now and transform all of these inequalities to inequalities that we can graph, meaning solve each one for y, like we did in our last section that we practiced with. So go ahead and solve each one for y, and then I want you to pause this and come back, because when I graph it, I already have it as y is less than or equal to or greater than or equal to, depending on what it's supposed to be, if we're flipping the sign or not. This is how I graph it. So I'm going to pause now. All right, so now I'm talking, you should have those already solved. So now again, here's our graph, and you kind of see, okay, I have the lines already graphed. We already did this with equals, but now you're gonna see I'm gonna start shading. You're gonna see how we're crossing off things, right? So here at 32, here's our y-intercept at positive 32 up here. Our slope is -2, meaning we're gonna go down 2 and to the right 1, down to the right 1, and then here's our line here. It says that it's greater than or equal to. Remember, greater than, okay? That actually should be less than. My apologies. So let me change that now. This should be less than. So when you pre-type your notes. Okay, so that's less than, I apologize. So that should be less than or equal to. Then now and notice how it's supposed to be less than, so we're crossing off everything above. Our next constraint says y is less than or equal to negative x plus 18. So 18 is our y-intercept. And we're going to go down 1, the right 1, down 1, right 1, because that's our slope. And it says is less than or equal to, so that means we want to cross off everything above. So notice how it keeps getting shaded above. Next constraint says y is less than or equal to negative x over 3, which there is a 1, so our slope is negative 1/3. 12 is our y-intercept, so 12. We're going to go down 1 to the right 3, down 1 to the right 3, so it's less steep. But it says less than or equal to, so we want everything below, so we're going to cross off everything above, right? So it'd be all above this line here. Cross off. And then our last constraint said that we want positive values. So that means that we're now only in this first quadrant, because this is where x and y are both positive. So this right here, this white section that is not crossed off or grayed out, this is what we call our feasible set or our feasible region, meaning that all of these values are part of our production schedule. Any value in there, in that non-shaded region, anything in there we can make in one day with all of our constraints. And then the only summary bullet point that I have is that it asks us to find pointer points in the feasible set or region that basically satisfies all the constraints. Next section, we'll look more at we want to make sure we maximize what we are doing.